Hello, class. In this video, we're going to talk about limits as x approaches to infinity. Now, the idea of infinity is kind of mind-bending. So in this question here, I've got what is infinity? Well, infinity is, first and foremost, didn't choose my pen. There we go. Is not a number. Okay. Infinity is this idea that we extend towards bigger and bigger numbers, never reaching an end. It is not a number. It is a concept. It is a concept. Now, that being said, we'll have to think of it like a concept, but we'll sort of kind of be using it like a number. And we'll look at that when we get to more examples. So really quickly, pause the video, write down this definition. Limits as x approaches infinity. A limit as x approaches infinity is an indication that a horizontal, slant, or other type of asymptote exists within the graph. I should say could exist. Okay. It's not automatic. You can do limits at infinity for polynomial functions, and you're not going to get a horizontal asymptotes out of those. All properties that apply to limits also apply if x approaches infinity, provided the limit exists. So these were our properties when, say, limit as x approaches infinity, that's messy, of f of x plus g of x is equal to the limit as x approaches infinity of f of x, and I'm going to have to write down here, plus the limit as x approaches infinity of g of x. So just those types of properties is what I'm talking about here. It works for sum, product, difference, quotient, and quotient provided that the limit of g of x is not equal to 0. It works for infinity as well. And again, provided the limit exists. Okay, so some basic limit properties. Now this one right here in the upper left-hand corner is the key one that we're going to be using today. The limit of sign does not exist. Now, this is not our traditional does not exist. In the past, we've looked at, say, graphs that look like, maybe I can draw it, maybe I can't. There we go. Where we have like a part of a graph there, and then it jumps up, okay? That will be one type that does not exist. Now, it could also technically not exist if it is approaching positive or negative infinity, because again, infinity is not a number. But sign's different because the oscillating nature of sign means it bounces between 1 and negative 1. So while the technical answer is does not exist, we have to think of it as it doesn't exist because we have a constant that's changing based on where we're at on the x-axis. Same thing for cosine. Tangent is plus or minus infinity. Cosine is minus plus infinity. Notice that if it's heading towards positive infinity, it'll be negative infinity because those graphs always go downwards. Secant and cosecant, and really this goes for tangent and cotangent as well. Keep in mind we have constant asymptotes along those graphs. So you could just as easily say for tangent, cotangent does not exist. Go ahead and write these ones down. These are functions that will approach positive or negative infinity at all times. Okay. For our second set, we have the limit as e of x, or e to the x approaches infinity equals infinity. But if it trends towards negative infinity, then it'll equal 0. The opposite is true of e to the negative x. If it's trending towards infinity, then the limit will be 0. Think about why. The exponential function is trending upwards like that, and whereas e to the negative x is trending downward like that. So it basically flips, and so we get opposite limits. The logistic function is trending towards 1 as x approaches infinity, and then trending towards 0 as x approaches negative infinity. These are the same as were on the previous slide, so you don't have to write those down again. Now, any logarithm. First of all, let's start with the fact that when we talk about logarithms, we're always talking about bases greater than 1. You could have bases between 0 and 1. That's not against the rules of logarithms. But generally, when we look at them in class, we only have bases that are greater than 1. Okay? So it trends towards infinity. Now, we don't talk about the logarithm as x goes to negative infinity because of the nature of a logarithmic graph. We could talk about the limit as x approaches 0 from the right, which of course go towards negative infinity, but that's for a different lesson. This is just x approaching positive or negative infinity. Okay, let's go over some examples. So, the limit as x approaches infinity. Now, typically my mindset for all these problems is plug in first. So let's tell you what happens if we get that. So we got 2 times infinity squared minus infinity plus 3 divided by infinity cubed plus 1. Now, let's just kind of go through this and see why it's mind-bending. Infinity squared. Well, again, infinity is not a number, so we have to think just not in terms of infinity, but really large numbers. And as those really large numbers are squared, what happens to those numbers? They become even bigger. Then if we multiply them by 2, they're going to become even bigger than that. So we effectively then get out of this infinity minus infinity. Now, it might be tempting to say infinity minus infinity is 0, but remember, this yielded a quote-unquote larger infinity than this one right here. So we actually will still have some level of infinity, and then plus 3, which is infinity, and then infinity cubed plus 1. So what we ultimately end up with is infinity over infinity. Now, this becomes a lot like the 0 over 0 situations. We can do something about this. So I'm going to rewrite the problem. The limit as x approaches infinity of 2x squared minus x plus 3 divided by x cubed plus 1. So the trick here is we're going to multiply by 1 over the highest exponent. So the highest exponent here is x cubed. So we're going to multiply this whole thing by 1 over x cubed. Now, obviously, what we do to the bottom, we must do to the top. So 1 over x cubed. So let's go ahead and distribute this. We got 2x squared over x cubed minus x over x cubed plus 3 over x cubed, all divided by x cubed over x cubed plus 1 over x cubed. Now, you may feel comfortable doing this in your head the more practice you get, and that's perfectly all right, but I just want to show you step by step how this is going to work out. Well, if we see 2 x's will cancel from here and 2 will cancel from here, 1 will cancel from here and 1 will cancel from here, and then none will cancel from here. We're good there. This will all simplify to be 1, and then that's good. Now, let's go ahead and rewrite that. That's the limit as x approaches infinity of 2 over x minus 1 over x squared plus 3 over x cubed all over 1 plus 1 over x cubed. Now, this is where, hold on, there we go. This is where this limit comes into play. A constant over a power of n will always be equal to 0. That's what these are. We've got a constant 2 over a power of x, which is 1. The power is 1, so x to the first. A constant 1 over x squared, a constant 3 over x cubed. These will all individually have limits equal to 0. And then same thing for this bottom one here. Now, it's very tempting because we said 0 a lot to say, oh, the limit is 0. Well, no, we've got 0 up top, but we got 1 plus 0 on the bottom. So we have got 0 as our final limit. Okay. So that's the trick. We're not going to be plugging infinities in. Let's just go ahead and continue our new trick. Our highest exponent in the denominator is 1. So we're doing 1 over x times 1 over x. And this time we're going limit as x approaches negative infinity this time. X times 1 over x, that's just equal to 1. And then 4x over x, that's just equal to 4 minus 2 over x. Now this limit right here will go to 0. And so we got the limit as x approaches infinity, or negative infinity, pardon me, of 1 over 4, which is just 1 over 4. Okay, great. Let's try another example. This time, well, once again, our largest exponent in the denominator is 1. Okay. So 1 over x. Multiply this whole thing by 1 over x. Okay. So we got the limit as x approaches infinity of 5x squared over x. That'll just give me 5x. 3x over x, that's just minus 3. Plus 12 over x, all over. X over x is just 1, plus 2 over x. We can take our limits that go to 0, and then we've got something over 1. So when we rewrite this limit, we'll rewrite it as the limit as x approaches infinity of 5x minus 3. Now, there's a couple ways you can work on this. Once you've simplified, remember, the trick is we substitute first. If we get 0 over 0 and now we're adding infinity to infinity, then we will do some sort of algebra, depending on the scenario. We'll simplify, and then we will resubstitute. So if we will resubstitute here, we get 5 times infinity minus 3. Okay? 5 times infinity is just infinity, and minus 3 is still infinity. So we've got a limit that goes towards infinity. But also, 5x minus 3 is, hold on, there we go. It is a polynomial. And polynomial, as x goes to infinity, this will go to positive infinity. It's still worth finding out, is it going to be positive or negative, but still. Okay. So that's that problem. Now let's go over this set of examples together. So we still apply the same thought process. We're going to multiply this whole thing by 1 over x. Now this is a tricky one because we can't do the same thing in the numerator. If we multiply by 1 over x, we won't be able to simplify anything because just 1 over x can't get into the square root. It doesn't have a ticket. It can't get into the club. So we need to make an adjustment. Well, if it needs a square root to be able to distribute into the square root, we'll go ahead and put a square root there. But square root of x is not the same thing as x. We want it to be equivalent to x. And that would be if we made it square root of x squared. Now, real quick note, remember that the square root of x squared is equal to the absolute value of x. But since we're trending towards positive infinity, we can drop the absolute value signs and just go with the positive of that. Okay? So this is the limit as x approaches infinity of square root of 16 over x squared plus x squared over x squared all over, and now this is just regular 4 over x minus x over x. So this is 1. This will go to 0. Oh, there we go. And then this will go to 0. And then this will go to 1. So we've got the limit as x approaches infinity of the square root of, well, we actually don't need the limit notation anymore since we're simplifying. This is 0 plus 1 over 0 minus 1. 0 plus 1 is 1. Square root of 1 is 1 over negative 1. So our final answer is just negative 1. Okay. Now, same idea here, except now we're going to negative infinity. So we're going to multiply this by 1 over x. Okay. Now this we're going to go ahead and do 1 over negative square root of x squared, since we're on the negative side this time. Well, it'll effectively get us the same thing. So we get the limit as x approaches negative infinity of the negative square root of 16 over x squared plus x squared over x squared all over 4 over x minus 1. So again, this is 1. This, if it'll work, is 0. And then this right here is 0. So we've got the negative square root of 0 plus 1 over 0 minus 1. Now we're going to have a negative 1 up top and a negative 1 down bottom, which is going to give us positive 1. All right. Example 5. Now we may want to remember that the limit as x approaches 0 of sine x over x is equal to 1. Pardon me. But now we're headed towards infinity. Well, if we were to simulate it by plugging it in, sine is of infinity over infinity. Well, what we effectively have, remember that as x gets bigger and bigger and bigger, sine just goes through this process where it's switching between positive 1 and negative 1. Pardon me. So what we have is we can write it as plus or minus 1. It might not even be that. It might be somewhere in between there. Over infinity. Well, when we increasingly expand our denominator, we're going to get 0. Okay. Same idea with 1 minus cosine x over x. So we get, now this doesn't count as a rigorous proof, mind you, but 1 minus cosine infinity over an infinity would be 1 minus plus or minus 1. Hold on, let me erase that. Again, doesn't count as a rigorous proof, but this is kind of the mindset behind it. 1 minus 1 is 0. Well, then it's just 0. 1 minus negative 1 is 2 over infinity is still 0. Okay. Go ahead, pause the video. See if you can attempt this example real quickly, and then we'll go over it. Okay, so the thing I'm going to do to start this problem is I'm going to split this into 2 fractions. I'm going to get 5x over x plus sine x over x. Now, as we just discussed on the previous page, this whole limit right here is 0. Okay, so we just get the limit, and these x's cancel, of x approaching infinity of 5, which the limit of any constant is just 5, and we're done. All right, go ahead and give the exit ticket a chance. Let me know if you have any questions. Thanks for watching.